like to introduce Rebecca Flitcroft. Again, as it says in the chat room, if you'd like to ask a question, please type it in the chat room and Rebecca will address them.
Well, good morning, everyone. I'm happy to be here this morning to speak with you about a project that a group of us has been working on that considers the effect of wildfire on two fish species, bull trout and spring Chinook salmon. In particular, we're going to be looking at wildfire and climate change for bull trout. We know that wildfire has been and continues to be a dominant process in the U.S., particularly in western states. Wildfire and other disturbances affect changes in upslope and aquatic habitats. In aquatic systems, disturbance is an important mechanism for the delivery of coarse sediment and wood into the stream channel. We expect the frequency and magnitude of disturbance events to vary depending on location within the river network. Smaller, low-order stream reaches tend to experience high-magnitude events with time to recover between events. Middle-order streams that are the repository of disturbances from smaller-order streams tend to experience higher magnitude events with greater frequency than low-order streams. High-order mainstem stream reaches may be expected to experience relatively low magnitude events but at a high frequency, reflecting the fact that these areas experience the cumulative effect of disturbances throughout the stream network. Disturbances such as wildfire, or the shallow landslides precipitated by wildfire, contribute wood and an array of sediments to streams adjacent to the disturbance. These materials become the building blocks of in-stream habitat at the site of the disturbance and throughout the river network as water sorts and transports material downstream. Since the Great Fires of 1910, the policy of the U.S. Forest Service has been the suppression of all fires. The fires of 1910 burned approximately 3 million acres of forest in northeast Washington, the panhandle of northern Idaho and western Montana, and killed 87 people, including 78 firefighters. We know that the policy of fire suppression has changed the fire return interval and the intensities of fires when they occur. Specifically, the size of U.S. wildfire appears to be increasing. The past suppression of fire that facilitated buildup of fuels is further compounded by changes in precipitation patterns and summer air temperatures across the western U.S. that is associated with the long-term patterns of climate. Further, the composition of forests is also changing as a result of climate and harvest practices. In this recent work from Merschel, Spies, and Heyerdahl, we see that the structure and composition of mixed conifer forests has changed in the past century in interior forests of Oregon. In this portion of the work, the composition of grand fir is shown with a considerable reduction in large tree density and a high density of small trees currently on the landscape. Although elements were different, similar patterns were evident in shade-tolerant Douglas fir and ponderosa pine-dominated forests. What does this mean for native aquatic species? There is an emerging view in the scientific community that wildfires may not necessarily be negative for fish and aquatic ecosystems. In fact, periodic fires may contribute to the long-term persistence of some fish populations. There are limits to this, of course, such as where populations of a species or subspecies are restricted to small areas and isolated from other populations. Several authors have described in detail the specific effects of fire on aquatic habitats. As summarized by Dunham in 2003, fires destabilize riparian vegetation, causing decreased stream channel stability. There is greater and more variable river discharge. Changes occur in the delivery of coarse woody debris from fire, and there can be increased nutrient availability. Higher sediment delivery occurs as a result of landslides. The loss of riparian vegetation results in increased solar radiation, which can in turn alter water thermal regimes. As we consider these effects of wildfire on aquatic habitats, it becomes important to consider where fish fit in. In this figure, Dunham and co-authors put fish into a context of vulnerability based on the ecological needs of the species. It is important to recognize that vulnerability of fish populations is closely tied to their specific behaviors, life history needs, and habitat requirements. So, as with many forms of disturbance, fire can be beneficial in terms of the creation and maintenance of habitats, but this has its limitations and is species specific. Species vulnerability to fire exists along axes of habitat size, isolation or its opposite, connectivity, and degradation. Species that are more vulnerable to fire tend to have specific habitat requirements. This vulnerability is increased if those habitats are also small in size and easily isolated within the stream network. The objective of this project was to provide decision support tools for managers to be able to assess the potential impact of fire and fire management on threatened and endangered species. We chose to focus on bull trout and spring Chinook salmon. As I will discuss later, these two species have radically different habitat and life stage needs, leading to different potential vulnerabilities to fire. The three objectives of this work were to first, develop methods to map habitat suitability for bull trout and spring Chinook salmon throughout a watershed. Next, we used wildfire, sediment, wood, and thermal models to predict changes in post-fire habitat suitability. Lastly, we evaluated the vulnerability of bull trout and spring Chinook to wildfire, answering different questions that were relevant to each species. Bull trout occupy cold water river and lake habitats. They are piscivorous and have been called the wolf of the stream system. Their predatory nature has led to eradication attempts in many portions of their range. They can exhibit either a migratory or resident life history and are currently only found in 21% of their historic range. Their need for cold water habitats tends to place their distribution in higher elevation areas. Bull trout are listed as threatened under the Endangered Species Act. This map displays a portion of the status review by the U.S. Fish and Wildlife Service from 2008. Core areas were classified as a combination of population status and potential threats. Warmer colors are more imperiled. Black are extirpated. Chinook salmon are the largest Pacific salmon in the U.S. They exhibit an anadromous life history, meaning that they spawn in freshwater and migrate to the ocean to grow into adulthood before returning to their natal streams to spawn. They are generally characterized as having one of two life histories. Spring Chinook migrate back to freshwater in the spring and hold until spawning in the fall. Their progeny spend between 1 and 2 years in freshwater before migrating to the ocean to complete their growth. This life history is often referred to as river type. Compared to the river type life history are fall Chinook that exhibit a different pattern of freshwater use. Fall Chinook return to spawn in the fall. Their juveniles generally migrate to the ocean to rear within a year after emergence and usually within 3 months. This life history is often called ocean type. Both spring and fall Chinook are listed as threatened and endangered in much of their current range. We focused our study in the Wenatchee River Basin of central Washington, located on the east side of the Cascade Crest. The Wenatchee drains into the Columbia River and contains ESA-listed populations of bull trout, Chinook, and steelhead. This area is characterized as dry with mesic forest and snowmelt-driven hydrology with peak flows in May and June and low flows in winter. Several large fires have occurred in the Wenatchee River watershed in recent years, including one in 2012 that was very close to the city of Wenatchee. The Wenatchee watershed has experienced similar land use and management as we find in other systems in the West, including fire suppression, timber harvest, grazing, climate change, the accumulation of dead wood, and dense forests. So how do our species of interest fit into a wildfire analysis story? In our case, bull trout have the specific habitat requirement of cold water. This tends to place them in smaller stream systems that have great potential for isolation within the stream network. This compares with spring Chinook salmon. These fishes tend to occupy lower river habitats with less vulnerability to isolation. Because spring Chinook hold in fresh water and their juveniles may rear in fresh water for up to 2 years, the need for river habitat for spring Chinook is still critical. We chose to use a Bayesian belief network as our analytical approach. This provided formal decision support to evaluate relative differences among management decisions and in assessments of population vulnerability. Outcomes are expressed as probabilities in a Bayesian belief network. Some advantages of a Bayesian network approach is the ability to directly incorporate and track uncertainty. We can integrate qualitative and quantitative information. We can also predict relative differences in outcomes across multiple scenarios. Bayesian nets are easy to modify to include new information or knowledge. One drawback of this approach is the absence of a scaling mechanism. Our approach was to assess pre-fire habitat suitability for bull trout and spring Chinook independently. Nodes in the network were physical factors that contribute to habitat suitability for bull trout and spring Chinook. Functional relationships were developed using statistical models or expert opinion, and I'll speak about these things more specifically coming up. Bull trout we assessed population vulnerability using two spatial scales, the reach and the larger habitat patch. The input metrics that were important at the reach scale included stream temperature, scour likelihood, gradient, and stream size. At the habitat scale, barriers, patch size, and connectivity were important considerations. For spring Chinook, habitat was modeled for each of three life stages: for adults, eggs and fry, and juvenile overwinter habitat. We used two spatial scales for this work, in this case the reach and the subwatershed. For each life stage, different physical features were considered to be critical. For adults, holding and spawning was combined with temperature and fine sediment. For adults, holding and spawning habitat are important. For the egg and fry life stage, the geomorphic suitability of habitat was combined with temperature and fine sediment. For the juvenile overwinter life stage, we also modeled geomorphic suitability and wood recruitment. Habitat suitability was calculated continuously across the Wenatchee and combined GIS, geospatial models, and output from NetMap. From here, I'm going to go into the details first of the bull trout models and then the spring Chinook models. After I've talked about the bull trout model, I'll pause, and so if you have some questions, I'd be happy to respond to them at that point about the bull trout model. As I've just described, vulnerability for bull trout was modeled as a combination of reach and patch scale factors. Each circle in this figure represents a model node and the general relationship between nodes. In the overall bull trout vulnerability model, we included reach scale habitat suitability, that's those variables in the white dashed box on the upper right. Results from habitat suitability enter the model in terms of the degree of expected change in habitat suitability post-fire and how good the habitat was to begin with. We didn't want to call something highly vulnerable if it wasn't good habitat to begin with. Vulnerability was modeled as a function of local fire effects on individual reaches and included fire severity and likelihood. The recolonization potential, or the potential of a reach to be recolonized from another patch following fire, and resistance, or the potential of a reach to be recolonized from within the same patch. In all this, the belief network allowed us to evaluate each model individually. We also estimated uncertainty in state classifications for all nodes. Next, I'm going to talk through the fire and thermal models that we used in the bull trout modeling and for spring Chinook. A critical input variable in our modeling was the prediction of fire probability. The fire simulation model we used is an extension of a FlamMap model developed by Paul Hesburgh and others at the U.S. Forest Service PNW lab in Wenatchee. The model was parameterized using current vegetation characteristics in the Wenatchee, topography, and was run using different wind directions with random ignitions. Model output was a surface of most probable fire severity, flame length, as well as how likely a fire is to occur. The stream networks that we used were a combination of the National Hydrographic Dataset digital streams and streams derived using NetMap software. Relationships between reaches were modeled using the flows tools in ArcGIS to create a network to measure distances from place to place. To predict stream temperatures, we used remotely sensed data available from NASA's MODIS satellite. This platform measures visible and infrared radiation reflected from the land surface. This land surface emissivity was spatially continuous throughout our study area and available over a 10-year time period in daily or 8-day increments. This figure shows the satellite band and the location of the Wenatchee watershed within it. We compared land surface emissivity, or what I'm going to call LST, with in-stream temperatures from 50 temperature logger sites in the Wenatchee River watershed. Land surface emissivity is not the same as land surface or air temperature. Using regression, we found a strong relationship between LST and in-stream water temperatures. We felt confident that the LST could be used to help us temperature in a temporally continuous way. The relationship we found between LST and temperature loggers allowed us to expand our prediction of thermal conditions throughout the entire Wenatchee River watershed. We next explored how the intensity of fires would affect LST. Using fires previously mapped and assessed for fire intensity by the Forest Service's Monitoring Trends and Burn Severity program, we were able to look at the effect of fires of different severities. The resolution of the Monitoring Trends and Burn Severity dataset was finer than the LST models, so we first averaged the fire intensity maps to the 1 kilometer resolution of the LST datasets. We were able to identify changes in land surface temperatures in high, moderate, and low intense severity fires. We developed a prediction of stream temperature at low, moderate, and high intensity fires and fit a hinge function to this relationship. Then we could take our estimate of current conditions and map our predicted thermal condition post-fire. In this figure, we're only displaying thermal conditions after a high severity fire, but with our methods we can look at any predicted fire intensity and the anticipated thermal effect of that fire on water temperature. It is important also to note that because our thermal relationships come from the MODIS imagery, we were able to model thermal effects at 8-day increments throughout the year so that we could consider important biological metrics such as degree days exposure. Now that I've described some of our key input metrics, it's important to get back to the bull trout model. As we developed our multi-scale approach, we delineated reaches, valley segments, and patches. One important question we had was, how do we define habitat patches for bull trout? Others have used elevation as a surrogate for water temperature. But as I've just described, we had modeled in-stream temperature, so we chose to use that. Patches were identified as the downstream most extent of maximum temperatures, and everything upstream of that was the patch. Determining the downstream most extent of maximum temperature meant looking at the thermal tolerances of bull trout. Juvenile bull trout growth is maximized at about 13 to 14 degrees Celsius and drops off sharply after this. Considering that fish still survive at higher temperatures, we conservatively identified a maximum pre-fire downstream temperature of 17 Celsius to delineate our patches of habitat. Our bull trout model included 3 elements: local fire effects, external recolonization potential, and internal recolonization potential, making vulnerability a combination of local variables associated with fire effects and patch scale factors associated with external and internal recolonization. I will go into a bit of detail about each of these elements. Local fire effects include the likelihood and severity of wildfire and the pre- and post-fire suitability of in-stream habitat for bull trout. Habitat suitability was based on aspects of the physical environment that have been shown to predict the occurrence of bull trout. There are 3 criteria that we had for the factors that we considered. They needed to be robust, peer-reviewed, and generally applicable across the range of bull trout. It was also important that the variables chosen were available across all streams in the Wenatchee Basin. We identified 4 important indicators. Stream gradient. We identified a threshold above which bull trout are less likely to occur. Scour, which we assessed from Vic hydrologic models developed by Seth Wenger and colleagues. we calculated the number of days in which winter flows are above the 95th percentile. More days above the 95th percentile is worse. Maximum water temperature came from the model that I've already discussed, and size. Our pre-fire bull trout habitat suitability models identified areas higher in watersheds as having higher suitability. In these images, we have displayed all the reaches with their suitability in the map to the left. In the map to the right, we have identified the areas of high habitat suitability and displayed the stream reaches with their upstream drainage because the polygons are easier to visualize. The result of the local fire effects model included habitat suitability and predicted fire intensity. This map shows no influence of connectivity, and the result does not change across scenarios. Areas in warmer colors indicate locations with high fire effects. This translates into areas where fire is anticipated to be likely to occur, to be severe when it does occur, and are located where bull trout habitat suitability was high before the fire. The next element of the bull trout vulnerability model was to assess external recolonization potential. To get at external recolonization potential, we needed to measure how far along the stream network a fish would need to travel from one patch of high-quality habitat to recolonized habitat in a neighboring patch. To get at this among-patch connectivity in the Wenatchee, we inventoried impassable barriers identified as culverts, waterfalls, or other natural features. In this figure, the map shows reaches above impassable barriers in red, and you can see the polygons associated with high-quality bull trout habitat. Clearly, there's a lot of overlap between areas that are isolated and suitable bull trout habitat. In this figure, we have mapped the potential for reaches to be recolonized from another patch. This incorporates the distance to the nearest patch, the number of road crossings they have to pass en route, and whether the reach is above an impassable barrier. This last feature carries the most weight. For example, the majority of Icicle Creek is above an impassable barrier, so recolonization potential from a neighboring patch is low. The next element of vulnerability is internal recolonization potential. For this, we were looking for the length of high-quality habitat available continuously within a patch. In our analysis, patches with more continuous high-quality habitat pre-fire have greater potential to have internal recolonization than patches with small amounts of high-quality habitat. We reasoned that areas with large amounts of high-quality habitat are less likely to lose all the available high-quality habitat in one fire than areas with limited or patchy amounts of high-quality habitat. Looking again at Icicle Creek, this basin has a large amount of connected high-quality habitat within the patch, making the internal recolonization potential high. The vulnerability estimate for bull trout brought all of these three pieces together: local fire effects and patch scale variables associated with external recolonization potential and internal recolonization potential. Our final vulnerability map indicated that generally, areas in the headwaters had a higher vulnerability to wildfire than areas lower in the watershed, often because of the importance of recolonization potential. Interestingly, our models indicate that even though Icicle Creek is above a barrier, it has a lot of good habitat and fire effects are low relative to other places. Because we used a Bayesian network, we could also map how certain our model results are. You can see that our uncertainty in some areas is quite high, particularly in the headwaters and the Icicle watershed. Because climate change is anticipated to modify in-stream temperatures, we were also interested in the potential effect of climate change on population vulnerability of bull trout. To assess this, we modified the boundaries of our patches with our 1, 2, and 3 degrees Celsius increase in temperature. You can see that the size of the patch boundaries fracture and become smaller with each successive increase in stream temperature. When we compared pre-fire habitat suitability among current conditions and climate scenarios, we found that the length of stream classified as highly suitable declined dramatically. Under the low climate change scenario, we anticipate 21% of current conditions in terms of high quality habitat, with declines from there. What factors are driving this decline? Based on the model sensitivity analysis, temperature was very important, which is not surprising. Interestingly, we see a big change in hydrologic metrics with timing shifted to fall and winter that also influenced this result. With regard to fire and climate change, one of our metrics of vulnerability for bull trout was the amount of contiguous high-quality habitat within a patch. Currently, the mean amount of contiguous high-quality habitat is higher than average fire size and even a conservative 25% increase in future fire sizes in the Wenatchee Basin. However, under all climate change scenarios, patches of contiguous high-quality habitat are smaller than mean fire size, thereby increasing the risk of a single fire burning an entire patch of high-quality habitat. When we look at the vulnerability of bull trout to both wildfire and climate change, by including the different patch sizes, we see that the constrained patch extents are universally vulnerable. In this figure, we are showing the current vulnerability that you saw earlier on the left, with vulnerability of the most extreme climate change scenario on the right. Interestingly enough, our uncertainty associated with the climate change scenario is consistently lower than with the current climate scenario, meaning that we are much more confident that these results will be what we see into the future. And finally, we looked at results of vulnerability classification under management and climate scenarios. Sorry. So finally, results of vulnerability classification under management and climate change scenarios. No management reflects fire conditions that continue as currently predicted, and that we have no management that may mitigate the effect of fire. Connectivity is management that removes all man-made barriers to migration. Fire size is management that keeps fires from increasing beyond current size. And both combines increasing connectivity with the maintenance of current fire sizes. Percentages in the first column are the proportions of all reaches classified as highly vulnerable, meaning that they have high habitat suitability and high fire intensity. Increasing connectivity decreases the proportion of highly vulnerable reaches by over half for both current and climate change scenarios. Holding fire size constant in future scenarios also has a large effect on the low and medium climate change scenarios. Under the high warming scenario, there is essentially no highly suitable habitat, so vulnerability does not change with management. Our take-home message from this is that management can influence population vulnerability to some levels of climate change. And before I move to the spring Chinook habitat, I had said that I would pause to see if anybody had any questions up to this point. So I'm going to wait for just a minute, and if you have any questions, you're welcome to type them into the chat, or I'll just continue along and talk about the spring Chinook habitat model. Hi, Jeff, I see you've raised a hand. Could you type in the chat box? Ah, I see you're typing. Perfect. Hi, Jeff. Are you still typing? I can't tell. It says that he's still typing, but I don't see any question. Oh, so we have a couple people typing. Thanks for your patience, everyone. Oh, they need to. When you're done typing, you need to hit the little box that has a little, like a bubble associated with it on the right so that I can read the message. When you put your cursor over that, it should say send. Well, I think I'm going to move on for now, but please keep track of your questions and I'll see if I can answer them at the end. So now I'm going to move on to our model of spring Chinook salmon. Spring Chinook, as was mentioned earlier, are large anadromous salmonid. Because spring Chinook are highly mobile as adults and by nature are distributed in areas that are accessible, we did not focus on isolation as an important driver for this population. Rather, we were interested in exploring their distribution in relation to fire. In this map, we have displayed the streams that we modeled in dark blue, the areas historically used by spring Chinook in orange, and the current distribution of spring Chinook in black. After we completed our modeling, we were able to compare habitat characteristics among these three distributions. In the spring Chinook salmon models, we also used a multi-scale modeling approach. At the reach scale, we modeled habitat quality pre and post fire by combining geomorphic characteristics, predicted quantities of fine sediment, wood input, and stream temperature as was appropriate for each life stage. We then assessed fire effects at subwatershed scales. For the spring Chinook model, we used the thermal models that were described earlier for bull trout, but also developed two additional models to predict the effect of fire on in-stream sediment and wood availability. In the spring Chinook model, we assessed habitat for the adult, the egg and fry, and the juvenile overwinter life stage. As with the bull trout model, each oval in this figure is associated with a model node. Different combinations of metrics were used for each life stage. Outside the Bayesian network model environment, we calculated a geometric mean across all life stages to capture an overall assessment of habitat quality. In the fine sediment model, we first modeled sand sediment yield to stream channels. This was done with NetMap software using a 10-meter digital elevation model and topographic index that considers slope steepness and hill slope geometry. The topographic index was converted to basin annual sediment yield by referencing the estimated basin average sediment yield. To convert predicted sediment yield to the fraction that is sand and finer, we applied soil texture classes that include the percentage of sands in soils. Next, we needed to know a factor of increase in erosion and sediment yield due to fires. We estimated this relationship between by multiplying flame length predicted by our FlamMap models and the increased rate of erosion or sediment yield. The predicted post-fire sediment yield is converted into sand sediment yield and is transferred to channels. The final step is to convert sand in channels to an average depth, both pre and post-fire. The percent increase is then calculated. In general, the highest values correspond to where predicted high flame lengths overlap with the steepest topography and with soils that contain large proportions of sand. Fire-killed trees are delivered to streams as a result of toppling, debris flow, or other mass transport events. The wood recruitment model predicted the effect of fire on wood supply to channel segments. The approach was based on calculating the wood mass balance, including the effects of forest growth, death, and tree fall. The lemma forest cover data were used to estimate live stem density per unit area to determine the number of potential conifer and hardwood trees that could become snags and subsequently fall into streams after a fire. The FlamMap models provided flame length that allowed us to estimate burn severity. Most probable flame length was associated with tree mortality. Using a random tree fall trajectory in the wood recruitment model, the availability of wood pre and post fire was estimated for each channel segment in the study watershed. Now we can get back to the habitat of each life stage of spring Chinook salmon. I would now like to briefly go through each of the life stage models. In the adult spring Chinook habitat model, we first identified channel segments with geomorphic suitability for adult spring Chinook by combining channel type and D50, which is a variable that describes sediment size. During summer months, adult spring Chinook salmon require cool holding habitat. While we would ideally have been able to use our thermal models to represent summer cool water refuge habitat, we felt that the resolution of our thermal data set did not represent the microhabitats that spring Chinook have been documented to use during summer conditions. Therefore, we modeled large wood because of the importance of wood in creating deep pool habitats. We modeled thermal conditions only during the spawning season because at this time in their life cycle they do not rely on microhabitats to meet their thermal requirements. The final model of adult habitat indicated potential increases in habitat quality in some areas post-fire. Because this is hard to see in the large figure, I have zoomed into a portion of the Chihuahua River. In this close-up, you can see that a section of the river has changed from predominantly moderate habitat quality to high-quality habitat. This increase in habitat quality was characteristic of adult habitat post-fire and is the result of higher quantities of large wood that should provide cover and deep pools as holding habitat. The egg and fry habitat model assessed spawning habitat geomorphic suitability. Since these are the places that eggs are laid, it was important for us to take the geomorphic suitability from the adult models into consideration here. We also included sediment and thermal estimates. In the final model of egg and fry habitat, we found potential decreases in habitat quality in some areas post-fire. As with the adult model, I have zoomed into a portion of the Wenatchee Basin, in this case to the main stem of Nason Creek. In this close-up, you can see the shift from high quality to low quality habitat post-fire. This decrease in habitat quality was characteristic of egg and fry habitat post-fire and is associated with the increases in fine sediment predicted in our models. The likelihood that a stream segment would provide overwintering habitat for juvenile spring Chinook salmon combined a channel segment's geomorphic potential and large wood recruitment. The final model of juvenile overwinter habitat indicated potential increases in habitat quality in some areas post-fire. As with the prior two models, I have zoomed into a portion of the Wenatchee Basin and in this case, a portion of the White River. In this close-up, you can see the shift from lower quality habitats to higher quality habitat post-fire. This increase in habitat quality was characteristic of juvenile overwinter habitat and is generally associated with the increased quantity of wood anticipated post-fire. Within the distribution of spring Chinook salmon, the overall pattern in the amount of high-quality habitat by life stage indicates a decline in egg and fry habitat, but increases in juvenile and adult habitat post-fire. We combined each life stage into a geometric mean for overall habitat quality for spring Chinook salmon pre and post-fire. In this figure, the geometric mean of habitat quality has been displayed. Of particular interest is the figure on the far right that shows the overall change in habitat quality throughout the modeled extent of the Wenatchee River Basin. Areas in blue in the figure on the right indicate potential increases in habitat quality, while red indicates decreases in habitat quality. Much of the changes occur outside of the current distribution of spring Chinook salmon. We were interested in how adult spring Chinook use currently available habitat compared to areas in their historic distribution. A statistical comparison of pre- and post-fire mean habitat quality for the current distribution, the historical distribution, and the area that was used historically but that is no longer part of the current distribution showed different potential responses to fire. The result I would like to draw your attention to is the statistically significant difference between currently occupied areas and those areas that were once occupied by spring Chinook, but that are no longer part of their current distribution. A statistically significant difference was detected in the geometric mean between these two extents, with lower geometric mean values in the historically used areas. We interpret this to mean that as the distribution of spring Chinook salmon has decreased, they are currently selecting areas with the highest pre-fire habitat quality and shying away from areas whose response to fire may not be as positive. In this figure, we have mapped just areas of high geometric mean. The dark pink lines are the area of the current distribution of spring Chinook. In this figure, I'd like to point out the small amounts of currently available habitat in the Pashastin and Icicle watersheds that are separated from the bulk of high-quality habitats in the Wenatchee River Basin. They are also in close proximity to non-Forest Service lands in the lower reaches of the basin that are transitioning towards the city of Wenatchee. This is important as I look at some sub-watershed results in the next few slides. When we look at the predominance of available high-quality habitat at the sub-watershed scale, the juvenile life stage generally has the lowest percents available. However, it is the juvenile overwinter stage that may offer the greatest increase in the availability of high-quality habitat post-fire. So, can fire be used or is part of a focus for restoration? There are some watersheds where the percent increases in habitat quality post-fire are quite dramatic. The Icicle and White Little Wenatchee systems are examples of this. However, because the Icicle Creek Basin has such a small amount of available habitat, restoration in this system may not be effective. In the Pashastin watershed, where so little habitat is already available, the potential effect of wildfire to alter habitat quality is very limited. It is also useful to keep in mind that the Pashastin and Icicle Creek watersheds are closer to the city of Wenatchee, thereby limiting the practicality of considering wildfire as a potential means of improving habitat quality. In summary, bull trout population vulnerability has the potential to increase post-fire. Climate change will negatively affect bull trout, but our results indicate that management that increases stream connectivity and decreases fire size may have an important mitigating effect. By comparison, our models indicate that wildfire can have a potentially positive effect on spring Chinook salmon habitat quality for the adult and juvenile overwinter life stages. The increase in juvenile habitat, which comprises the smallest amount of high-quality habitat in our models, may provide a compensatory mechanism for the negative effect we predict for the egg and fry life stages. Further, spring Chinook seem to currently be occupying those portions of the river system where the most positive response to fire is predicted. The conclusions of our work show that the effects of wildfire depend on the ecology of the fish species in question. Further, the physical effects of wildfire vary depending on local watershed characteristics. The effects of wildfire may be both positive and negative within a watershed, and gains in habitat quality from wildfire from one species may be a reduction for another. I'd like to acknowledge the Joint Fire Sciences program that funded the majority of this work, the Wenatchee National Forest, and a suite of individuals whose participation in this work has been instrumental. And with that, I would like to try to open this up for questions again. I see somebody is typing. Hello, so I see a question from Tom. Do you consider the effects of climate change on spring Chinook as you did for bull trout? In this analysis, we did not consider the effects of climate change on spring Chinook as we did for bull trout. Particularly, we did not do that in this instance because the thermal regime was such an important characteristic in our determination of patches with bull trout that it was a key element that we could consider there. Including climate change for spring Chinook is something that we could certainly do in the future and is something that we would like to consider doing in the future as well. The other element about climate change for spring Chinook that we would like to include would be additional VIC modeling and hydrologic modeling, and include that in the model for spring Chinook. So Shannon Clausen has written in, what kind of time frame are you thinking for increasing habitat post-fire? That's a really good question, because what I didn't talk about here was the time frame for when we would see habitat responses post-fire. In the literature, we would expect to see results from fire occurring within the first 3 years post-fire. The other thing to keep in mind is that the negative effect of sediment on the egg and fry life stage may be a relatively transitory effect. In other research, native fish have been found to recover from fire within as soon as 4 years. So the long-term potential of fire to contribute structural habitat forming material may have a longer-term effect on the stream channel. Looks like somebody else is typing. So it looks like someone is still typing, so I can just chatter and wax poetic for a few minutes here. Um, I think, Shannon, that your question about the time frame piece is really a particularly important one, and that's an element that we could try to include in our modeling, especially with the thermal response of streams to fire. I didn't present the as much of that as I could have, but we did see in our thermal modeling the result of fire being lasting longer than we might have expected in the land surface emissivity from the MODIS satellite imagery, so thermal conditions don't necessarily recover quite as quickly, perhaps, as the sediment conditions that you might expect to see in the streams. And I see Tom's question. Would you consider summer habitat for both adult and juvenile spring Chinook if you did use climate change models? It seems that summer temperature will be a limiting factor for spring Chinook in the future. Yes, I think that the the thermal condition for spring Chinook, especially in some of the lower portions of their range, will have great potential. We were It was unfortunate that the resolution of our thermal models was so large because holding spring Chinook do hold in very small microhabitats. They are very adept at finding thermal refugia in the summer. So finer resolution with the thermal data set would help with this. But I think that you're right. Once we bump up the thermal temperature in the streams, then the potential for those refuges would decline as well. Some work that would look at the availability or the distribution of thermal refuge habitat would really help with that piece of it. And the same, if we were to include summer habitat for juvenile spring Chinook, the thermal piece would also be an important one. Again, they are also good at finding those thermal refugia, but as that lower part of the system really warms up, there will be much more limited places for them to go. All right, well, at this point, I will just ask if anybody else has any more questions. And if you'd like to get in touch with me to talk about the details of any of this any further, I'm very happy to talk about this work. The bull trout models were published in the Canadian Journal Fisheries and Wildlife in January of this year, and the spring Chinook model is in prep for publication. So that one will hopefully be coming out within the year.
Well, thank you, Rebecca, very much. And that's it for the webinar. Thank you all for participating. As it says up here, we will be posting this webinar on our website, so you can view it again or have colleagues that were unable to attend this morning view it. So anyway, thank you very much, and we'll see you next time. Bye.